So good evening everyone. Welcome all of you to the week 11 discussion of this course, Computer Vision, and this course was originally taken by Professor Jayanta Mukhopadhyay, Professor Computer Science and Engineering Department, IIT Kharagpur. My name is Ayan Paul. I am a PMRF research scholar from IIT Kharagpur, and my duties are I am a PMRF TA for this course. I will be discussing problems that are very similar to your assignment, so that whenever you will be solving your assignment, it will be very easier for you. But before that, always I prefer to discuss some of the summaries that has been discussed in this week before moving on to the question answer part. Okay. So let's start the discussion. So today we will be uh, discussing something regarding dimensionality reduction. Okay, so what is this dataset dimension? So dimension of the data refers to the number of features, attributes or variable used to describe each sample. Okay, so that is the definition of dimension. Again, I am repeating, dimension of data refers to the number of features. Features can also be called as attributes or variables used to describe each data sample. Example, a point xy in 2D space, that is dimension 2. Okay, because we are representing that that data point by two axes, that is, one is your x axis and the one is your y axis. So a point xy in 2D space has the two dimension. Okay, so x axis is one feature or attribute or variable, y axis is another feature or attribute or variable for the data. Okay, so that is how that is what is known as the dimension of data. Okay, a image of size 28 cross 28 pixel flattened as dimension 784. Okay, a dataset with features like age, height, weight, income, that is 4 dimension. Okay, so that is regarding different examples of dimension. Okay, so regarding image, because we are discussing computer vision, so if it is called, it is a 28 cross 28 pixel image, so how many dimension it has? It has 784 dimensions. So each image, like if your data set has 60,000 image, so each image has this 60,000, each image has this 784 different axes or 784 different dimension or 784 different feature, or also called attributes. Okay, so that is a dimension of your image. Another thing is regarding you must have seen various chart regarding person name is written, and then different attributes are written like age, height, weight, income. Such type of sheet you must have seen again and again. So if like a person age, height, weight and income is written, so how many dimensions are there? 1, 2, 3 and 4. So that data set has 4 dimensions. So formally, if each data point is represented by a vector, this, so xi1 xi2 dot 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 xid, so this has the d dimension data, because it is attributed by 1 to d dimension, so that is why d dimension data. Okay, so that is regarding data. What is the dimension of data? Okay, now this is regarding yeah, this is another representation, you can also see in it. So you can see this is a image. Okay, or this is a image, and this red color points are data points. And to represent this data, how many axes we are using? One axis, two axis and three axis. So if this is x axis, this is y axis, this is z axis, so this data point is represented by 1 2 3 4 this 4 data points are represented by 1 2 3 axis. That is, this dimension, this data set has 3 dimension. Okay, 4 data points and 3 dimension for each data point. Okay, but you can easily see in this image, even if you can see this 4 data points are represented by three axis or 3 dimension, you can easily see that 1 2 3 4, this the spread, the spread is actually in 2 direction. Okay, so if we can just slide a plane in which all these 4 data points are lying, so this is the plane in which all the 4 data points are lying, so we can reduce the dimensionality of the data. Earlier the dimensionality was 3, but we can now reduce the dimensionality of the data to 2. Okay, because plane has 2 dimension. Okay, So that is why like xy plane, yz plane, zx plane, so all has two dimensions. So if we can slide a plane to this four data points, we can convert the dimensionality from 3 to 2. Okay, so that is another thing. Like if we change the, so what we are learning, if we are changing the dimension, or if we are changing the axis, that the axis feature, whatever you say, if we are changing the feature, we can project it into another feature and we can thus reduce the dimension. Okay, now you must be thinking why we are concerned about the data dimension. Okay, if the 4 points are taking 3 dimensions, so okay, why we are so concerned about it? So that is the one of the question. So first point is curse of dimensionality. As dimensionality increases, the data becomes more sparse. What is sparse? Sparse is each, in linear algebra, each data point can be expressed as a linear combination of different vectors. Okay, like if you are representing a data like x, y, z is your data, and you have this three vector, you have this three vector, x1 vector, x2 vector, and x3 vector. So any data point x, y, z can be easily represented in this by this different vectors. Okay, by all linear combination of different vector. So that is the thing. Now if we are increasing the dimension of the data becomes more sparse, means more vectors are required to represent the data. So that is a problem. And the thing is regarding distance matrix. The distance matrix then becomes less meaningful because so many axes we are projecting. So many axes, so this distance matrix then becomes less meaningful. And then model may overfit because they can memorize high dimensional noise. Now more dimension means some of the dimensions are less critical, so there can be more noise. Okay, so example, in 1D 100 points cover space well. In 100D they barely scratch the space. Okay, so that is the thing. Like in 1D, if you are representing 100 points, they cover space well. But if you are representing just 1 point with 100D dimension, then they barely scratch the space. Means we are just wasting the space and we are representing just 1 point. Same thing, right? If 100 points are there, we are projecting in 1D, and if 1 point is there and we are projecting in 100D. So if 1 point is there and we are projecting in 100D, we are just consuming the space. You can just literally think we are just consuming the space, right? We do not require those 99 dimension, right? Because we have one data point, we can easily represent it in one dimension only, but we are just wasting the other 99 dimension. Okay, so that is the thing. So this is regarding curse of dimensionality. The second, computational complexity. More dimension, then we have larger matrix, means each vector. I have told you sparse representation means linear combination of vector. Data point represented as linear combination of vector. So more dimension, it will become more sparse. So large matrix are required and higher cost for training and inferencing. So whenever you are taking that data and whenever you are just training it for machine learning algorithm or deep learning algorithm, so you require to form large number of matrix. Okay, so the computational complexity will certainly increase in training the data. Example, training a neural network of 4K image is very expensive. Okay, so that is because 4K image is 4K, that is 4000 only, but each image can have this 784 dimension. Okay, so if in place of 784 dimension, if we can project this data in like 2 dimension or 3 dimension, so we can reduce this computational complexity cost. Okay, so this is another thing. Third is regarding redundancy and irrelevance. Not all features are useful. Some may be noisy, correlated, or irrelevant. Okay, for example, you are taking like for selecting a individual in a team. Okay, so you are taking like irrelevant data. For example, yeah, for selecting person in a sports team, okay, how many match he has played is okay, height, weight is okay, because that may be required, but like number of houses he have, that does not have any influence on how he will play, right? So this is just noisy thing. Okay, it does not require, it will just make your computational, it will just make your cost more computational expensive. Okay, so that is another problem. Fourth, generalization. High dimensional data increases the risk of overfitting, reduces dimensions, improve the model's ability to generalize the unseen data. Okay, so high dimensional data increase the risk of overfitting. Yeah, so if you have high dimensional data, it can certainly increases the risk of overfitting. So reducing dimension improves the model ability to generalize to unseen data. Okay, so that is another thing. Yeah. So this is regarding why we are concerned regarding the data dimension. And last point is definitely visualization and interpretability. Okay. So like if you have so many dimension, 100 dimension, you are only representing 25 data, but you are using 100 dimension. So definitely 100 dimension you cannot visualize. A human eye or human can only visualize either 2D or 3D dimension max. Okay, so again, if you are just projecting your data in 100 dimension, it does not gives you a better visualization or interpretability. You cannot visualize it. That is why what we do is we generally intend to only choose like 2 or 3 dimension at max. Okay, because that gives us better visualization and interpretability. Okay, so this is the introduction. Imagine classified fruit based on color, weight, sweetness, size, etc. 4D. Okay, that is 4 dimension, because color, weight, sweetness and size, means we are classifying it into 4 dimension. Okay, so that is the thing. So adding irrelevant feature like day of the week or random noises increases the dimension unnecessarily. So this makes the classifier less efficient and less accurate. Okay, so that is why we do not require more dimension. We want to project our data in as much less dimension as possible, but condition is keeping all the variance of the data. We do not want to lose the variance, but we want our data to be in as many less dimension as possible. Okay, so that is regarding data dimension. Okay, and why we are concerned about data dimension. Okay, so this is the thing regarding the data dimension and why we are concerned. So now our idea is to decrease the dimension of data. So how we do? So we have a popular dimensionality reduction technique known as principal component analysis, PCA. Okay, so what is this PCA? It reduces the dimensionality by finding a new orthogonal axis. So I have already told you, like in this example, that to reduce the data, to reduce the dimensionality of data, we have to project it into different bases or different axes, or you can say different feature or attribute, like that, right? Earlier this data has 3 dimension, x, y and z, but now we are projecting it into a different dimension. Okay, so by that we are only explaining this data set in only 2 dimension. Okay, this axis and this axis, we do not know what axis, but let's say this is x dash and let's say this is y dash. Okay, so in place of x, y, z, we are just projecting this data set into 2 axes, that is x dash, y dash. Okay, so that is the idea behind the principal component axis, finding the new orthogonal axis. So what is this orthogonal axis? Orthogonal means these axes are uncorrelated. So whenever like x, y, z, the axis that we are using, these axes are actually uncorrelated. Okay, means x does not have any relation to y. Or orthogonality in mathematical sense, the x vector dot y vector will be equal to 0, or x vector dot z vector is equal to 0. Okay, so that is orthogonality, or this axis does not have any correlation with each other. Okay, so that is orthogonal. And the data has the maximum variance or spread. Okay, so by this we will choose our orthogonal axis. So again I am repeating, PCA, it reduces dimensionality by finding new orthogonal axis called the principal component, along which the data has maximum variance or spread, and these axes are uncorrelated. Okay, so that is why it is known as principal component analysis. The axis that it will choose the data to be projected, this axis is known as principal component. Okay, and this principal component is such that the data has maximum variance, and this principal components are, or this axis are uncorrelated or orthogonal. So PCA transform the data set into direction of maximum information while discarding noise less important directions. Okay, so this is the thing. Yeah, mathematically you can see this, but let's explain it how you have to implement the PC algorithm. Okay, so you can just focus over here: data matrix X with n sample rows and D feature columns denoted rows xi t, means x data are there, x rows are there. That x rows means x data are there, x1, x2, x3, x4, like x n datas are there. Okay, and that is in the rows. Okay, and columns are nothing but all the features or all the dimensions. Okay, so first thing is what we do is we center the data, that is we just find out the mean of all the data points, like x1 plus x2 plus dot 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 xn divided by capital N, and capital N is the total number of data points. Okay, so just we find out the mean of the data, and then we, after finding the mean of the data from each data point, what we do, we just subtract this mean. Okay, that is known as, that this step is known as centering of data. After centering of data, we find the sample covariance matrix. Okay, so covariance matrix is calculated by this formula. Okay, 1 by n minus 1 xt x bar. Okay, so by this x bar t and x bar is nothing but centered data. Okay, that means data set minus the mean of each data point. Okay, so by this we find out the covariance. Once we find out the covariance, we decompose it to eigenvector and eigenvalues and eigenvector. The sum of eigenvalue will tell you the total variance of the data, and the eigenvector are the principal axis along which our data should be projected. Okay, so that is the whole theory. So two things, after eigenvalue decomposition of this covariance matrix, we will get two things. One is eigenvalues, second is eigenvector. Eigenvector, the sum of eigenvector will give the total variance of the data. Okay, and eigenvalue of each eigenvector, that will give you the variance of the eigenvector. Okay, so that is the point. And each eigenvector is the principal axis on which you will project your data. Okay, so what we do, we generally do not take the whole eigenvalues, because if like 100 eigenvalue, if the matrix is 100 cross 100 and we are taking all the eigenvalue, so that will not give us the dimensionality reduction. But we try to take the eigenvalue, like we out of 100 we will take only 10 eigenvalues. Okay, and other 90 eigenvalues we will ignore. Okay, we will ignore or we will eliminate. So just 10 eigenvalues. So now out of this 100 earlier we have 100 dimension, but now we will project it into 10 dimension, or the 10 highest eigenvalues. How we choose it? We choose it along the variance ratio, means how many eigenvalue we should choose. That we choose it like how much percent variance we require. Okay, so eigenvalue we will just put it in descending order, and we will choose according to how much variance we required. For example, we required 85% variance, so we will see how many eigenvalues we should take in the numerator and divided by all eigenvalue in the denominator. Okay, so by that we will see that how much eigenvalue we should take to get 85% of variance. Other eigenvalues we will just ignore. So that is how the principal component analysis works. Okay, so so now your question can be, why eigenvectors and eigenvalue? That is a main question, that why eigenvector and why eigenvalues. Okay, so this is the concept of eigenvector. So like this sigma is your covariance matrix that we have just found. Vi is the eigenvectors for this, and lambda is the eigenvalue for this. Okay, so that is a simple thing, that like we write a lambda av equals to lambda v, right? That is our equation of the, or characteristic equation. Av equals to lambda v, where v is your eigenvector, lambda is your eigenvalue for a matrix. Okay, now a matrix we do not require, we are taking eigenvalue and vector of this sigma matrix. Sigma is the covariance matrix. Okay, So the eigenvalue lambda tells how much data varies along the eigenvector direction. Okay, so that because of this theory we are doing the principal component analysis by this way, because each eigenvalue lambda tells how much data varies along the eigenvector direction. Okay, so eigenvector of the covariance matrix will give us the direction in which variance is measured, and eigenvalue tells us magnitude of variance in those directions. The largest eigenvalue vector is the direction of maximum variance, first principal component. Second largest eigenvalue is the orthogonal direction with next highest variance of the second principal component. Okay, so that is the thing. And second thing, we know each eigenvector that you will calculate, they are orthogonal to each other. Okay, so orthogonal to each other means are this property that the axis should be as uncorrelated as to each other, so that is fulfilled. Okay, so that is another reason. So this is why we choose eigenvectors and eigenvalue for such principal component analysis. Okay, so let's explain you by an example, numerical example, that will be better clear. So this is these are your data point. Okay, data point 5, 3, 2, 4, 6, 0, and 1, 2, 3, 4, 5 data points we have. Okay, perform PCA if applicable, reduce the dimension of the data. So now we are using 1, 2, 3 dimension, but they have told that perform PCA and if applicable reduce the dimension of the data, that we have to do. So how we proceed? This is our total data matrix. How we write the data matrix? Each data point we represented by a column, like 532, so this is your first column. 460, this is your second column, like third, fourth, and fifth column. So we have this 5 data points, and we are representing like this. Okay, now calculate the S bar matrix. That is nothing but mean of each column. Okay, so mean of each not mean of each column, but mean of each row. Okay, so that you have to calculate. So 5 plus 4 plus 3 plus 2 plus 3 means 9, 12, 14, 17. 17 by 5, that is 3.4. Similarly, you can calculate second row, add it and divide it by 5, because you have 5 data points. Similarly, third column, you just add it and divide by 3. So by this you will get the mean. Once you got the mean, what is your step? You have to center the data. That means you have to subtract the mean from each data point. Okay, so just this data point you just subtract the mean, this data point you subtract the mean, this data point similarly you just subtract the mean. Once you got the X bar matrix, that is nothing but centered data matrix, you can easily get the this covariance matrix. Okay, so covariance matrix, this is the formula. By this you can easily get your covariance matrix. Once you got the covariance matrix, trace is very easy. That is the total variance of data, that is nothing but the sum of diagonal. That is actually sum of eigenvalue or sum of variance, but see, the matrix has the property that sum of diagonal elements will also give the sum of your eigenvalues. Okay, so either you first just calculate this eigenvalue and eigenvector from this, and then you just add all the eigenvalues and you will get this same thing. Okay, and you have to ultimately calculate the eigenvalue, so better just calculate the eigenvalue and eigenvector from our covariance matrix. Okay, so these are the 3 eigenvalue you will get. One is 83.328, second one is 1.5562, and third one is 0. That means in third direction we do not have any variance of the data. That means, of course, third direction we do not want, because third direction it does not have any variance of the data. Okay, so that is why third direction we do not want. And these are your respective eigenvectors. Okay, these are your eigenvalues and these are your eigenvectors along which you have to this project your data. Okay, so these are the 3 eigenvectors, and you can write this eigenvector by this equation, by this matrix, combined matrix. And this combined matrix, when you will multiply with your this centered data, these are the results that you are getting. Okay, that means in the third direction you are getting 0, 0, 0 point. In third direction we do not want it. Okay, so ultimately what we have done, we have only projected a dimensional data. We have this 3 dimension. For each data point we have this 3 dimension. Now ultimately we have projected a 3 dimension data into only 2 dimensions. Okay, because third dimension is there is no variance along third direction, so definitely we are just ignoring the third direction. Okay, so that is regarding the principal component analysis. Okay, now what are the application? These are some of the application. We can do data compression. Definitely we are compressing the data because we are reducing the dimension, so we are just compressing the data. Okay, and then decorrelating components. So again, I have told you, as we are projecting the data points into eigenvectors. Now this eigenvectors has this orthogonal property, means they are uncorrelated. Okay, so you are not doing nothing but you are decorrelating the components. Earlier, either if some components are correlated with each other, you can once you perform the PCA, all the components are decorrelated. Okay, so that you can use in all this multispectral, hyperspectral and ultraspectral remote sensing, because multispectral means you have this tens of band, hyperspectral hundreds of band, ultraspectral thousands of band. But the problem with all this camera, when you will use the data you will get, they are actually correlated to each other. But to study the property, we want our properties to be completely uncorrelated. Then only we can study, right? Like from this first band, like we have this 10 band, and all this 10 band gives us a combined data. So definitely we cannot study. But if one band give us uncorrelated data, then only we can study it. Okay, so that this is the another example of our PCA, that is, it decorrelates the component. Okay, because we are projecting it into a principal component that are nothing but eigenvector, and eigenvectors are always orthogonal to each other. Okay, so this is the thing. Third is regarding this factor analysis. So highly correlated factor useful for classification. For example, eigenfaces for representing human faces. Okay, so if we just you can say, if we just separate each eigenvector, what we can do is we can make different, like your image is a total face, like we are taking 60,000 image, right? And each image is a different person image. Then what we do, we just perform the principal component analysis. Okay, now principal component analysis, we will have as how many dimension, like each image can have like 784 dimension, right? 28 into 28 image means 28 into 28 pixel means 784 pixel for each image. So we will have this 784 different principal component. Now this 784 different principal component, what we can do is we can separate 784 different component, and then we can add one component. And we can experiment or make a face by adding different components. Okay, so that is known as eigenfaces. Okay, so perform PCA on a large set of human images, face cropped to same size. Any arbitrary face expressed as a linear combination of them. So any arbitrary face can now be explained as a linear combination of few eigenvectors. Okay, so coefficient of linear combination represents an arbitrary face. Okay, so that is how you can also do the classification. Okay, so PCA is this is the algorithm, you can see. So these are the images, then you do this factor analysis, and after that you can just add one principal component one by one, and by this you can do the classification, and then you can just get the output. Okay, so this is regarding PC. Okay, so one application I will also show during a coding during the last coding part. I will also show one application. Okay, so what I am telling by this, so that will be more clear. Okay, so what are the limitations? Okay, so let me ask, any doubt in this PCA? You can ask. Any doubt in PCA? How to perform PCA? Any doubt in calculations?
Nothing, sir. Go ahead.
Okay, nice.
Sir, sorry for the interruption. Is it 10th week class or 11th week?
This is 11th week, right? 10th week I have
11th,
taken.
yeah, 10th week already completed. So I listened and I solved some problems about 10th week. So that's what I am asking. Okay, sir, go ahead.
Can you please repeat?
10th week class is over, right?
10th week class is over, but I think the answer you will get on next Thursday, right?
Yeah, yeah.
Yeah,
Okay, sir. Okay.
yeah, yeah,
Understood.
yeah. So after that only I can release the answer from my side. Okay, means detailed answer from my side.
Okay, sir.
Okay. So what are the limitations of PCA? Now PCA has some limitation, particularly regarding classification. For the purpose of classification, dimensionality reduction using PCA may not work. Okay, so that is the one of the limitation of PCA. It captures the direction of maximum variance for a dataset. For labeled dataset, it does not capture the direction of maximum separation between the group of data points of different labeling. So that is what is the limitation of PCA. Though PCA captures the direction of maximum variance of the dataset, okay, that PCA captures, but PCA does not capture the direction of maximum separation. When we are just separating two classes, it will not give us the what is the separation between the group of data points, okay, with different labels. Okay, that PCA does not give us. So for that, we have this thing called Fisher linear discriminant analysis, or Fisher LD. Okay, so for two classes, okay, so for two classes, suppose we have the data points from two classes C1 and C2. We project the data on a line. This is a line on which we project the data. So now we want W such that the projected class means are far as possible, and the projected class variance are as small as possible. That is tight cluster. Okay, so by this image, what I want to tell is, whenever I will be separating or during classification, because to classify these two classes, what I need to just separate these two classes by a line. So I want this line such that the projected class means are far apart from each other. Okay, that is, each class will have some means, and this projected class means should be as far apart as each other, and projected class variance should be as small as possible. Means within the class, this variance should be as small as possible, but between the class, this variance should be as large as possible. So I want my W is nothing but the direction of this line to separate the both of the class. So that I require to have the linear discriminant analysis. Okay, so again I am repeating, PCA only what PCA does is it captures the direction of maximum variance for the data set, but the problem arise for the PCA was regarding classification. Okay, so classification for labeled dataset, it does not capture the direction of maximum separation, because whenever we are classifying, we want to have the direction of maximum separation. So that PCA does not give us. Okay, so for that we shift from PCA to this Fisher linear discriminant analysis. Okay, so linear discriminant analysis is, it is a type of classification. Classification means we will just find out a line that will classify the two groups. Okay, so binary classification is what we are discussing. So we will find a line so that the separation between the two classes will be more. But another thing is, the separation between the two classes should be more, but within the class they should be as close as possible. Okay, so to have a better cluster, or to form a tighter cluster. Okay, so that is linear discriminant analysis. Okay, so how we do the linear discriminant analysis? So this is known as measure of separation. Okay, so measure of separation, this has this formula, JW m1 minus m2 whole square divided by s1 square plus s2 square. Okay, so this upper thing, that is m1 minus m2 square. Now what is m1? M1 is nothing but you can say u1 is the mu1 is the mean of the data points belonging to the first class. Mu2 is the mean of data points belonging to the second class. Okay, This is nothing but you can simply say this is the mean. Okay, mean into what is your that projected axis is. Okay, so you can just ignore this, you can just simply think it as mean. Okay, that is mean of the first class, mean of the second class. So in the numerator, this thing m1 minus m2 square, m1 minus m2 whole square, that is nothing but the separation in between the two classes. Okay, so that is variance between class. Okay, variance between class. And in the denominator, that this is s1 square, that is scatter of class w1, and this is s2 square or scatter of class w2. Okay, so this in the denominator, that is scatter within the two class. So we want the scatter between the two class to be as maximum as possible, and scatter within the two class to be minimum as possible. Okay, because if our numerator will increase and denominator will decrease, then only we will get a better value of separation. Okay, because numerator if we just increase, then our value will increase, and denominator as we decrease, our value will again increase. Okay, so that is the idea of this Fisher disk LDA. Okay, Fisher LDA. So in matrix form, it can be written like this, JW. The same thing, it can be written like this. By this, if m1 is this and m2 is this, so it can be written like this. And here there is two things, SB and SW. So SB is nothing but this is the matrix for SB, and SW is nothing but this is the matrix of SW, that is S1 plus S2. So this is I have told you this in the denominator, this is nothing but scatter between the classes, and in the denominator, this is scattered within the classes. Okay, and how we can get the the solution W, that is the line separating the two classes, that can be found out by this thing. Okay, that is W star is nothing but SW inverse mu1 minus mu2. By this you can get the W star. So key difference between PCA and LDA: PCA chooses the direction that maximizes the variance, LDA chooses the direction that maximizes the class separability. So that is the difference between the PCA and the LDA. Okay, so this is the thing. So let's just discuss it by a problem, so that will be more clear. So how LDA and PCA is working, so that will be more clear to you. So data point x1 is this, has 3 dimension. Okay, 5 3 comma 2, 4 6 comma 0, and 3 minus 7 comma 14. Okay, so this is the first group, and this has this 3 data. This is the second group, and this has this 3 data. So perform LDA and get the optimum direction. Check the separability in the line of projection. Perform PCA on the whole data set ignoring class information, and get the dominant principal direction. Check the separability of projected point on the points on it. So that are the two questions. So first we will solve LDA. Okay, so LDA, as we have two classes, this is our first class and this is our second class. So in first class, this is our data point 5 3 comma 2, that we will project it like a column. 4 6 comma 0, second column. 3 minus 7 comma 14, this is the third column. And x2, we will project the data in this column, 3 columns. So minus 2 minus 5 comma 17, 3 minus 3 comma 10, and minus 4 minus 2 comma 16. These are the 3 points. Now how we will proceed? First we have to calculate mu1, that is mean of this first set, and mean of this second set. Okay, so how we will calculate mean? It is very easy. You will get the mean for each attribute. Where is the attribute? Attribute, always remember, attribute will be your column, will be your rows. Okay, so this is attribute, this is attribute, this is attribute. Okay, and this columns are nothing but your data points. Okay, so that is how you have to do. So for each attribute you have to see what is the mean. So 5 plus 4 plus 3, that are the attributes. Okay, so this attribute you have to see what is the mean. So 5 plus 4 plus 3, that is 9, that is 9 plus 3, that is 12 by 3, that is 4. So 4 is the mean of this attribute for this first, that is for this first data point, this is the first attribute. For this second data point, this is the first attribute. For this third data point, this is the first attribute. We will sum up and divide by 3. So that is how we can get the mean of the first attribute. Similarly, we can get the mean of the second attribute, mean of the third attribute. So by that we get the mu1, that is mean of the first class. Similarly, we calculate mean of the second class. Okay. Once we got mean of the first class, then mean of the second class, we can form this matrix. S1 will be this. Similarly, S2 will be nothing, just replace 1 with 2, that is x2 minus mu2 into x2 minus mu2 transpose. Okay. So by that you can form the S1 matrix and you can form the S2 matrix. And by this way you can easily form the SW matrix, that is nothing but S1 plus S2. But remember, your line is nothing but SW inverse. So what you will have to do, you have to find out the inverse of this SW matrix. Okay, so once you got the SW matrix, you just find the inverse of it. Okay, and then into mu1 minus mu2. What is mu1? This is mu1 and mu2 is this. So by this you can easily calculate what is your direction on which you have to project the data. And once you got the direction on which you have to project the data, you can easily project your data. Okay, so this is the first projection of this class x1. So by this you are getting this, and this is the second projection of this class 2, or the first projection of this class 2. So by this you can get the projected data. Okay, you just find out you have this x1, you have this x2, so you can find out this y1 and y2. Okay, so this is how you have done it. This is regarding LDA. Now we will see about PCA. Okay, so this PCA we do not have any information about class, so that is why PCA we have to write all the data points in one go. Okay, that is one set. So that is why we are writing only x. Again we will take the same thing, that is we will take the mean, but this mean we have to take for all the points. Okay, earlier we are separating classes, that is why we have two means, that is mu1 and mu2. Now we have only one mean, that is mu. Okay, so that we can easily find out 5 plus 4 plus 3 minus 2 plus 3 minus 4, that will be minus 4 cut, and 8 minus 2 6 plus 3 9. Okay, 9 divided by 6, that is 1.5. Similarly you can get the mean of the second attribute, mean of the third attribute. Okay, and by this, after this, what is your step? Your step is to center the data. So you have just centered the data by this way, and then you just find the eigenvalues. Once you got the covariance matrix, you just after that you have to form the covariance matrix. So I think it is not centered. No, it is not centered. This is the covariance matrix. So very easy. I have already told you how to find the covariance matrix once you have this. So covariance matrix, it is very easy. Covariance matrix, this is the formula to find the covariance matrix. So you will write there you have 6 data points. So 1 by 6 x bar t. Okay, x bar is nothing but the centered data. So once you got the this data, once you got this mean, you have to just subtract it from each data point to get the centered data. Once you got the centered data, 1 by number of data points, that is 6, and then you have to just write x bar into x bar. Okay, so by that you can just center the data, and after that you will form the eigenvectors. You will get the eigenvalues, and then you can get the eigenvectors. Okay, so by this you can try. So here what has been done, they have we have to show the difference between the LDA and PCA. Now they have done is they have just taken the covariance matrix for this class wise. Okay, so this is the covariance matrix of any one class, and similarly you can find the covariance matrix of other class, and after that you can do the separability. So here you can easily see the separability is less here and separability is more here, because LDA is known for classification. So definitely the separability will be more in your LDA than your PCA. Okay, so this is how is the difference between your LDA and PCA. So again I am revising this key difference. PCA choose the direction that maximize variance, so it does not include only no class info, but Fisher LDA or Fisher's LDA choose direction that maximize class separability. It uses the label. So that is the key difference between your PCA and LDA. Okay, so that is regarding your PCA and LDA. Okay, so any doubt in this? No doubt. right? Now we have this sparse representation. So I have already told you sparse is, this is the definition of the sparse. Yeah, a linear combination of only any data point can be expressed as a linear combination of basis vector. Okay, basis vector, basis is nothing but direction, like x y z. You have this three bases that has been used in your x y z coordinate system, right? So this xyz is also known as basis, or it can also be known as atom. Okay, so don't get confused by all this statement. So regarding dimensionality, each axis like xyz, that can be called as either axis or dimension or basis or atoms. Okay, anything it can be called. So sparse representation means representing a data point as a linear combination of only a few vector or whatever you can say, basis vector or atom from a dictionary instead of using all the basis vector. Okay, so that is sparse representation. Means whenever you are performing PCALD or whenever you are doing this dimensionality reduction, what you will do, you will only keep some principal vectors, right, and you will ignore the other. Okay, so then what you will do, you will express your data point as a linear combination of this principal component, not all the principal component but few principal component. Okay, so the result you will get, that is known as sparse representation. Okay, now the total number of vector is known as the dictionary. Okay, from a dictionary means total number of all the vector, that is known as dictionary, and from that dictionary we will choose only few atoms, because the idea is dimensionality reduction. Okay, so these are all terminology, so no need to just confuse regarding terminology, these are all same things. Okay, so consider a dictionary of n element, that is n dimension, so vector known as atoms. Okay, so same thing. So dimension dictionary means total dictionary. In this dictionary you have nothing but you have small n or capital N number of capital N number of total dimension, and from this you will only take small n. Okay, you will only take small n atom to represent your data point in those atoms. Okay, that is the idea of this sparse representation. Okay, so these are all the things that has already been discussed, same thing. So just yeah, these are all the dimension, and then you can just get your data point into b into y. B is nothing but the total number of vectors you are choosing, and this b into y. So actually it should be y equals to b into x. Okay, y should be your sparse representation, b should be all the data, all the dimensions that you are taking, and x should be your data point. So that is how we represents our sparse representation. Okay, so this is exact reconstruction, means if you are taking all the atoms, then this is your exact representation. Okay, that is alpha aj or alpha j into dj. Dj is all the atoms you are taking. So by that you can just do the exact reconstruction of your data set. But exact reconstruction if you will do, we are not performing dimensionality reduction. So our idea is approximate representation. So approximate representation, how you can do? You can do approximate representation by choosing some of the not all the n, but choosing a less number of atoms. Okay, so that is how you can do it. That is sparse approximation. Okay, so sparse approximation, what you have to do, you have to choose number of atoms or number of vectors such that this is also known as residue. Residue means this is your actual data vector, and this is your approximation, means ak, that is ak is your direction, dik is your direction rather, and ak is what is the vector you are representing. Okay, that is ak. Okay, that is ak into dik. So that is how that this is the residue. Okay, x minus this thing. Okay, this is nothing but this is approximation, because we are not taking all the dimension, but we are taking some of the dimension. So this is approximation. This is the approximated thing, and this is the actual data vector. So actual minus approximation or actual minus prediction, that is nothing but error. So this is also known as error or residual. So our task is to choose from a fixed number of atoms such that this we have to minimize as possible. So our sparse representation will give us the more give us or cover maximum variance of the data. That is our idea. Okay, so this is regarding sparse representation. So again I am repeating, any vector can be expressed as a linear combination of few basis vector atom from a dictionary. Dictionary means all the basis vector. Okay, basis vector is also known as atom, so all the basis vector is known as dictionary. But all the basis vector if we will take, then we are not doing any dimensionality reduction. Okay, so for dimensionality reduction what we have to do, we have to only take a few basis vector. Okay, so if we are taking like D is our total number of vector, that is the whole dictionary. That is the whole, sorry, D is like dictionary, and dictionary has total capital N number of atoms of the basis vector. From this capital N number of basis vector, we will only take small n number of basis vector, rest we will ignore. So by this we are doing a dimensionality reduction. But that we have to ensure that once we are choosing the small n, we have to ensure that this thing, that is error or residue, that should be as less as possible. Okay, so this is the actual data point, that is x vector, and this is the approximation, that is alpha z into di. Okay, that should be as less as possible. This residue should be as less as possible. Okay, with fixed number of atom, we have to ensure that this residue should be as less as possible. So for that we have this pursuit algorithm. So pursuit algorithm method that try to find a good approximate or the sparse solution. Okay, so that is the pursuit algorithm. Means pursuit algorithm ensure that this thing, that this residue should be as less as possible. Okay, that is the work of the pursuit algorithm. So how pursuit algorithm works? There are different type of pursuit algorithm. We have this MP or the matching pursuit, then OMP, then we have this BP. Okay, so MP is a greedy algorithm. Greedy algorithm means iteratively it pick the dictionary atom that has the highest correlation with the current residual. Okay, so current residual means if first step there won't be any residual. So first step how it operates is, it just multiply your data point with your basis vector, and it checks that for which basis vector it is getting maximum correlation. Okay, or maximum answer, you can easily say that maximum answer which it is getting. The answer for which it is getting maximum, then what it do, it try to minimize it. Okay, by then like first it will pick the like we have this v1 to v6 vector. Okay, so v1 to v6, what we will do, from our data point we will just multiply v1 to v6, and we will see for which vector it is getting maximum answer. Okay, then what we will do, once we get this, then our target is in the next step, then we once for first we have already done, and then out of the 5 remaining we will see again that which for this second 5, or it can also take, as it is a greedy algorithm, so sometime what is does is it takes all the 6 again. Okay, and then again it checks for which data vector it can get the maximum or the best approximation. Okay, so that is how matching pursuit works. So I am not going into the formula etc because it is confusing. So MP may select the same atom multiple times. So this is the con of NP. Okay, chosen atoms are not orthogonal. So this is the main disadvantages of MP, that the vector it is choosing, okay, this vector might not be orthogonal to each other. So as these vectors are not orthogonal to each other, so what is the problem? That these are not uncorrelated. Okay, because if the vectors are orthogonal to each other, then only it is uncorrelated. Okay, otherwise it is correlated to some extent. And if it is correlated to some extent, then what will it will happen, the next, like first it has chosen v1, but when it will choose v2, that v2 has some correlation with v1. So your target to get the minimum thing, that will not help. Okay, so to solve this, we have moved from this matching pursuit to orthogonal matching pursuit. Now what this orthogonal matching pursuit do, it clarifies, it rectifies this of matching pursuit. Okay, that matching pursuit, the chosen atoms are not orthogonal, but here it will ensure that the chosen atoms will be orthogonal to each other. Okay, so after choosing atoms, instead of just subtracting correlation, that is this part, recompute the coefficient via the least square fit, and ensure that will ensure the orthogonality. Okay, so that is the speciality of this orthogonal matching pursuit. Again, I am not going on this formula. So pros, it is more accurate definitely, but as it is doing one more step, it is more computationally expensive. So that is the next algorithm. Third, we have this basis pursuit. So basis pursuit, again, it do instead of greedy selection, it solve an optimization problem. Okay, so earlier we are just doing the greedy selection. We are just picking one, and we are seeing if the if we are getting the maximum answer of or not. But here it does not do the greedy selection, but rather it solves some optimization problem like this. Okay, so it uses L1 normalization to encourage sparity, solved via linear programming or specialized convex solver. Okay, so it chooses your vector not by simple greedy picking, but it's solved by some approximation error using L1 norm. Okay, so that is why finds global optimal sparse solution under condition cons lower than MP and OP algorithm. Okay, so again I am not going in detail, but this is the thing. Okay, so MP algorithm, greedy picks one atom at a time, simple, fast, coefficients not optimal, but then to solve this we have this OMP. Okay, greedy plus least square refit. Okay, so better accuracy, more computation, and then we have this last basis pursuit. So it solve the complex optimization problem to get your atoms, and best recovery under theory, slow heavy for large data. So yeah, so these are the theory. So again I am not going into theory, better just to see some question that will clarify your concepts. Okay, so consider the following set of basis vector. This is one basis vector, this is another basis vector, and this is a third basis vector. So basis vector and called nothing but atoms. Okay, so these are your three atoms. This is your first atom, this is your second atom, this is your third atom. Okay, so they form an orthonormal set of basis vector. Orthogonal means orthogonals, how you can find either two vector like v1 and v2. How we can find orthogonal v1 and v2? We will just do the dot product. If the dot product answer will come 0, then these vectors are orthogonal to each other or uncorrelated to each other. So you can just check this and this. So 1 by root 3 into 1 by root 2 means 1 by root 6, minus 1 by root 3 into 1 by root 2 minus 1 by root 6, 1 by root 3 into 0, that is 0. So 1 by root 6 minus 1 by root 6 plus 0, that is 0. So you can easily say that these two are orthogonal. Similarly, you can check this minus 1 by root 18 minus 1 by root 18 and 2 by root 18. So 2 by root 18 minus 2 by root 18, again that will be equal to 0. So these two are also orthogonal. Now check this and this, minus 1 by root 12 plus 1 by root 12 and plus 0. So again 0. So all these vectors are orthogonal to each other, but here it has been our orthonormal set. Orthonormals means first you have to check either they are orthogonal to each other, and second you have to check whether the unit or the magnitude of each vector is 1 or not. Okay, so you can just do the calculation and find unit vector for each, and whenever you will just put root over 1 by 3 minus 1 by 3 plus 1 by 3, you can easily say that is 1 by 3 minus 1 by 3 but the whole square. Okay, so that is 1 by 3 1 by 3 1 by 3, so answer will come 3 by 3, that is 1. So this is orthonormal, or this is a normal vector, and this also you can check, that is 1 by 2 plus 1 by 2 2 by 2, again same thing, and this also you can check 1 by 6 1 by 6 4 by 6, so again 6 by 6, that is 1. Okay, so this three vector are orthogonal to each other, and all these three vectors are unit vector, so they are orthonormal basis vector. Okay, so that is what has been written. Magnitude each vector is 1, and take any pair of vector, perform dot product, and you will get 0. So these three vectors are orthonormal basis vector. And then it has been told decompose a vector 1, 2, 3 as a linear combination of the above set. So this is your vector. Now you have to decompose it into a linear combination of these three vectors. Okay, so that you have to do. So very easy. How we will do? How we will do it is very easy. Just you have to multiply your vector, that is 1, 2, 3 is your vector. Okay, so that you have to multiply with each direction or each basis vector. Okay, so just multiply this by this and you will get the magnitude. Okay, this into this you will get the magnitude or coefficient you can say, and this multiply by this you can get the coefficient. When you get all the coefficient you can easily write like this. So your 1, 2, 3 can be expressed as expressed and is in this direction. Okay, that is 1 by root 3 minus 1 by root 3 1 by root 3, this direction. This is the first direction with this coefficient, this is the second direction, this coefficient, this is the third direction with this coefficient. Okay, so that is how you can express your this vector as a linear combination of the above three vectors. Okay, so that this is the thing. Okay, so this is the concept regarding how you can project the vector. So earlier 1, 2, 3 has been projected as what vector are projected as combination of are projected as nothing but combination of this three vector, that is 1, 0, 0. Okay, 0, 1, 0, 0, 1, 0 and 0, 0, 1, 0, 0, 1. That was earlier, it was projected like this with coefficient 1 for this, plus 2 for this and plus 3 for this. Okay, so that is how earlier it was projected, but now we have projected into a new basis like this. Okay, so that is what we are discussing. Now like this, if we just remove one vector like this vector we can just remove. Okay, so by that we are doing the dimensionality reduction. This would not be you won't get 1, 2, 3, but you can get closer to it. Okay, so you have to check which vector is not that important, that vector you can remove, and other two you can keep, or other one you can keep. By that you can get an approximate result. So that is known as sparse representation. Okay, so that is the concept of this. I hope you everyone understood it. Like if a vector is like this 1, 2, 3, then you can represent it like this. Okay, that is three orthogonal direction. This is the x orthogonal direction, y orthogonal direction and z orthogonal direction, with this magnitude for x, this magnitude for y and this magnitude for z. Okay, so this was earlier projection, but now what we have done, we have projected like this. How we have projected like this? Now we have this three vectors as our basis vector, this vector and this vector. So our magnitude will also get changed. Okay, earlier it was 1, 2, 3, now it was 2 by root 3, 3 by root 2 and 7 by root 6. How you got this? Just multiply your vector with your this direction. By this you can get the coefficients. Okay, so this is the whole logic behind your projecting any vector to some basis. Okay, so this is the whole idea behind it. So is it clear what I have told? Orthogonal, orthonormal, how we can project the vector in any directions. Okay, is it clear? Any doubt in this? This is very basic and this should be as clear as possible. Is this clear? Clear, right? Nice. So this is the thing. So let me just erase. Yeah, so let's move on to the next question. So this is the next question. Consider a dictionary in 3D space. This is the following atoms. Atoms is nothing but basis vectors. Okay, this and this. Okay, 3D space. So you will have 3D space, and you have this all this basis vector. Okay, 1, 2, 3, 4 basis vectors are given. Derive the best representation of the vector 1, 2, 3 using two atoms of the above dictionary following orthogonal matching pursuit or the OMP algorithm. Okay, so how you will do? First you have to project your this into all of this and see what the result you are getting. Okay, so when you are will be projecting all this into this, the result you are getting is 6. Okay, that is the maximum you are getting, like 1 2 1 plus 1 into 1, that is 1, 1 into 2, that is 2, and 3 into 1, that is 3. So 1 plus 2 plus 3, that is 6. Okay, but when you will be projecting here, so that this is 1 into 1 is 1, minus 2, that is minus 1, and 3 3, so minus 1, that is only 2. Here the answer is coming 2, here answer was coming 6. And let's see here, that is minus 1 minus 2 minus 3, and minus 3 and plus 3, that is 0. Here answer is coming 0. And let's check the last one, that is minus 1 minus 1 plus 2, that is 1, and 1 plus 3, that is 4. Here the answer is coming 4. Okay, so you will check, you will first take this direction. Okay, so this direction, once you have taken it, you have to just find out the residue. Okay, so residue, first residue how will calculate? This is your original vector, or this is your original data point, and you have to do this, that is minus magnitude that we are getting, multiply by this. So magnitude we are getting 6, and this is our first basis vector that we are choosing, so we are getting this. So after this, once the residue you are got, from this residue you have to again perform the same step. So minus 5 minus 4 minus 3, again you have to check which you are getting maximum. Okay, so again you have to check, so definitely these are all minus, minus 5 minus 4 minus 3, so here you will get minus 12, and then minus 5 plus 4. Okay, minus 5 plus 4, and minus 3. Okay, so again minus 5 plus 4 and minus 3, so that is minus 4. Okay, minus 4 you are getting in the next. And third, if we will check, that is 9, 9 minus 3 is 6. Okay, so third you will get the maximum. So now for this step you will choose this, so just choose this, and again you are getting this, and then you can easily perform the this thing. Okay, xy. So now how you will get the xy? You will get the xy by solving this. Okay, 1 2 3, these are the these are the two bases that we have selected basing on the maximum correlation with the residue. These are the two bases. Okay, first this is the first basis, this is the second basis. After that you have to find xy. So xy can be found out by this. Just take a vector like this and just do this calculation, and by this you can get the xy. Okay, so xy you are getting this and this. Okay, that is 18 by 10 and 6 by 10, and then you can project your vector 1 2 3 as this is your first coefficient, that is 18 by 10 or 1.8, 1.8 into this vector, and then 6 by 10, that is 0.6 into this vector. Okay, so that is how you are performing the OMP matching pursuit. Okay, so this is the whole idea behind it. So is it clear how we have done this? Any confusion, anything? Any confusion in this problem? Clear, right? Nice. Now let's move on to the next topic, that is learning a dictionary. So learning a dictionary, given a set of data points, that is this. Okay, xi in Rn, that is you will have this n dimensional data. What should be a dictionary D of k atoms, so that it would provide the best possible sparse representation for each member of set. That means you have to learn the dictionary. This dictionary should be good, then only you can get the k atoms. Okay, that the k atoms that will give the possible sparse representation. Okay, so this is the thing. If this dictionary that you are forming, if this dictionary is not good, then you will not get k atoms, so that it would provide best possible sparse representation. So again I am repeating, you have this data points, that is it has this n dimension. sorry, it has this n data points from 1 to capital N. So n data points 1 2 3 4 dot 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 n. Okay, so you have this not 1 2 3 4 literally like x1 x2 x3 dot 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 xn, means you have this n data points. Okay, now you have to form a dictionary. Dictionary means where you have all this basis vector, that is dictionary. Okay, so you have to what should be the dictionary that we have to find out, so that of k atoms, so that it would provide best possible sparse representation of each member of the set. That means first thing is learning a dictionary is important. If we know this dictionary, it would be easier for us to find the best k atom to get the best possible sparse representation. So that is the idea. Okay, so motivation, this is the motivation: use of dictionaries adaptive to specific classes of the signal or the data in interest. Okay, so if we can learn this dictionary based on our specific interest, okay, specific classes of signals or specific data of interest, so application would be specific. Okay, rather than forming different dictionary, if we know what is our like specific class for which the dictionary needs to be learned, then it would be more easier for us. Then dictionary learned from examples with sparse representation property ensured. Okay, so dictionary that learn from examples with sparse representation property ensured. So if we learn the dictionary from examples, that is the particular specific task we have with sparse representation, so the sparse representation would be easily ensured. So that is the thing. So then this is the thing, like yeah, this is the whole dictionary, and from that we will take only the small n number of atom, and by that we can get the best possible sparse representation y. Okay, so actually this is the thing, that is x equals to dy. D is the dictionary, means the dictionary with best possible atoms, and y is the y is the sparse representation of the atoms we are selecting. Okay, or the matrix of atoms that we are selecting. Okay, so that we have to ensure that this thing should be equal to this, or rather we can say x minus dy, that should be less than a possible threshold. If sigma is the threshold, that should be less than a particular threshold. Every concept is same. So for this, again, all this is theory, so again not very much important all this. So yeah, so this is the algorithm. So let me clarify the algorithm. I have told you, like we have this n data points, so xi, that is from I to capital N, so x1 x2 x3 dot 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 xn. Okay, so output is nothing but a dictionary that we want to achieve, so that yeah, the output is a dictionary that we want to achieve. So first initial dictionary of k atom that we perform, or that we find out by k-means clustering. Okay, once we find the initial dictionary of k atom, we have to again perform the pursuit algorithm to get the best possible out of the dictionary, and then iterate the updating j of atoms and sparse representation associated with the atom. Okay, so that we have to do. So in this we are iterating both. Once we are iterating in the previously, that is pursuit algorithm, we are iterating only the atoms, but here we are iterating the dictionary also by kmeans clustering, and then we are iterating the chosen atoms also from by this OMP algorithm. Okay, so what are the application? It is used for compression, denoising, deblurring, super resolution, mapping of learned dictionary, and implanting. Okay, so you can read this statement, that is very simplified. It has been told KSB is like teaching the computer a set of building block or dictionary atoms, so that any signal, image or sound, we are focusing about image, so any signal or image can be written using a few blocks. The sparse coding makes it powerful for tasks to compressing, denoising, and restore. So that is regarding the KSVD algorithm. So again I am repeating how this works. How this works. So first it forms an initial dictionary by your k-means clustering. Okay, and then once it forms an initial dictionary, in that given dictionary, to select the possible best atom, it perform the matching pursuit algorithm. Okay, and then again iterate a dictionary, again get the by the matching pursuit algorithm, it gets the best possible atom. So by that it gets a possible number of sparse representation, and it can choose which sparse representation is the best. So that is regarding learning a dictionary. Means here we are learning the dictionary also. We are not only learning the this atoms or the basis vector, but first step is learning the dictionary. So that is the added step here in this ksvd algorithm. Okay, so this is regarding this. So let's go into the question answer. Okay, so all this is theory, so again you can just read it, it will be better. So only question is for this OMP algorithm. So OMP algorithm, and how you are just projecting any data point into different bases. So these are the two type of question that you can encounter. Other things are all theory. So theory you can just learn, you can just remember that there are three basis algorithm, that is MP, OMP and BP, and then you have this KSVD algorithm that first learn the dictionary, and then uses the any MP algorithm like OMP algorithm. So that is the whole theory behind this. Okay, so topic on which week 11 assignment questions are based: dimension reduction technique, that is PCA and Fisher LDA, and then sparse representation, pursuit algorithm, and last dictionary learning and sparse representation, KSVD. So here you won't get much numerical related to it, but numerical you will get from the first three only. Okay, so let's just go to the question answer session. So consider the data point 4, 3, 1, 4, 5, 0, 2, 5, 3. Compute the covariance matrix of the set using PCA. Okay, so what should be the steps for it? First we need to form the data matrix. Okay, how we perform the data matrix? It is very easy. We write each data point as a single column, and number of this number of, you can say, number of dimension or number of feature as a row. Okay, number of feature should be in a row, and feature should be in a row, and your data point should be in a column. So by that we first write the data matrix. After that we do the data centering. Once we do the data centering, our covariance matrix is nothing but 1 by n x bar into x bar transpose. Okay, so by that we can get the covariance matrix. So it is very easy. So after getting the covariance matrix, you can just find out the this eigenvalue and eigenvector, and then choose the best eigenvalue that will best the eigenvalue, or just arrange the eigenvalue in descending order, and choose the number of eigenvalue you require to get the maximum variance. Okay, or the variance that has been asked in the question. So by that you can solve any PCA algorithm question. So here it is very easy. So just form the data matrix first. So this is your data matrix. Okay, this is your data matrix. So I have told you each column will represent your single data point 4, 3, 1. So this is your first data point. So first column with this. And attribute, this is your x attribute 442, 442. This is your x attribute. This is your y attribute 3, 5, 5, and this is your z attribute, that is forming rows. So this is your this is nothing but your x matrix or your data matrix. After you get this, you get the mean vector. Mean vector is very easy. Mean is regarding your attribute. So when you are talking about mean, so you have to see the attribute. So 442 is your first attribute. So what should be the mean? 4 plus 2 divided by 3, or 10 by 3. Okay, similarly 13 by 3, similarly 4 by 3. So this is your mean. Once you got the mean, you have to center the data. That is how you center the data. That is nothing but for each data point you subtract this mean. Okay, so 4, 3, 1, you subtract 10 by 3, 13 by 3, and 4 by 3. Okay, so by this you can get all your you can get this matrix or the centered matrix. Once you got that centered matrix, it is very easy. This is your covariance matrix. Okay, so this is your covariance matrix 1 by 3 A transpose. Okay, So this is very easy. 1 by 3, that is 1 by n, that is the number of data point, A into A transpose matrix. Okay, so by this you can easily get your covariance matrix. Okay, so this is how you have to proceed it. So very easy, I hope. Any doubt in this?
Sir, in step 1,
Yeah,
sorry, step 2,
yeah.
n equal to 1 by 3, how it is get, sir? 1 by 3.
Mean means what is
1
mean?
by 3.
Yeah, mean means 1 by 3. 1 by 3 is nothing but number of data point. How you calculate mean of, like, if I give you 2 comma 2 and 4 comma 5, how you get the mean? 4 comma 5. Okay, these are the data point, 4 comma 5. 2 comma 2, 4 comma 5. How you can get the mean? 2 comma 2, 4 comma 5. 2 plus 4 by 2, that is 6 by 2, that is 3, and 2 plus 5 by 2, that is 7 by 2, that is 3.5. That is mean, right? Am I audible?
Yeah, yeah, yes, sir.
Yeah, so that is how you get the mean, right? So 1 by 2 x attribute, that is summation of x attribute. So what is x attribute? 2 and 4, right? So 1 by 2, 2 plus 2. Okay, so 1 by 2 into 4, that is 2. Okay, and then 1 by n, that is here 2 data point I have given you. So 1 by 2, 2 plus 5, so 7 by 2, that is 3.5. So your mean is 2 comma 3.5, right? Got it? Hello?
Yeah, yes, sir.
Yeah, got it for this, right? Now it is very easy for this attribute. How you calculate it? It is very easy. 4 plus 2 divided by 3 data point, right? So 4 plus 2, that is 10 by 3. Similarly, 3 plus 5 plus
It's understood, understood.
yeah, yeah. So that is how you got the mean. After you got the mean, you have to center the data. That is x matrix. This is the data point matrix minus the mean matrix. So by this you get the centered data. And after that it is very easy. Just perform this. That is 1 by n. That is the number of data points into center matrix into transpose of the centered matrix. By this you can get the covariance matrix. Okay. So answer is 0.889 minus 0.443 1 point. I think A option is the correct answer. Okay. So option A is the correct answer. Okay. So this is how you have to solve it for PCA. So this is the first step of PCA. After this step, what you have to do? You have to find the from this matrix. This is the covariance matrix. This matrix you have to find the eigenvector and eigenvalue of this matrix. Okay, eigenvalue is nothing but your variance for each eigenvector, and eigenvector is nothing but your principal components. Okay, so that is how you have to do it. Now second question, from the data point given in the question 1, what is the total variance? So total variance, either you just calculate the vector and eigenvalues. The sum of eigenvalues will give you the total variance in the PCA. Okay, but also we know the matrix property. According to matrix property, the sum of eigenvalue is also equal to the diagonal of the matrix. Okay, so that is the property of any matrix. Okay, so that is why you can easily, once you got the covariance matrix, you can easily sum up the diagonal to get the total variance. So your total variance is coming 3.3.3.4. Okay, you can also check with finding the eigenvalues and eigenvector. Once you got the eigenvalue, you would just do the sum, you will get the same answer. Okay, so that is a matrix property. So by this you can easily get the total variance in PCA, and option is 3.3.6. okay, 3.3.4 is coming, so option B is close to it, so just marking option B. Okay, so option B is the correct answer. So is it clear what I have told? Yeah, nice. Question number 3, which of the following are true regarding the principal component analysis? It finds the minimum dimensional subspace for representing the data. All principal components are orthogonal to each other. It provides the direction along which data have the largest variance. It computes the component along principal axis. Computes the components along principal axis. So very easy. I think all of the above should be, or all of the above, or A, B, C, D is your correct answer. So it finds the minimum dimensional subspace for representing the data. So very true. Like PCA projects the data onto a lower dimensional subspace that capture maximum variance within minimal loss. So we can easily say this statement is true. And second statement, all principal components are orthogonal to each other. Yeah, principal component are nothing but your eigenvector, and eigenvector are always orthogonal to each other. Okay, so option B is also right. Option C, it provides direction along which data have the largest variance, so you can just compare the magnitude of the eigen values for each eigenvector. Okay, the eigenvector for which it has a maximum eigenvalue, you can say it provides the direction along which data have the largest variance. Okay, so that is what has been written. The first principal component corresponds to the eigenvector with the largest eigenvalue. Okay, this you should remember, gives the maximum variance direction. And option D, it computes the component along principal axis. So yeah, principal axis eigenvector of the covariance matrix PCA aligns with them. So option D is also correct. So option A, B, C and D are your correct answers. Okay, so this is complete theory question, so you can easily read and it is clear to all of you, I hope. Okay, so let's move on to the next question. LDA is a parametric method. Option A true, option B false. So yeah, LDA is actually a parametric method. So LDA, linear discriminant analysis, it is parametric. Again, it is a theory question. So it is because it makes assumption about underlying data distribution. So the key component of LDA, I have already told you in the previous class also, when we are talking about LDA for classification, right? So I have told you each class, LDA assume that each class follows this Gaussian distribution. Okay, and Gaussian distribution, you have this two things, two parameter. One is this mean parameter, second is this variance parameter or standard deviation parameter. Okay, so that is why all classes are assumed to have the same covariance matrix. So parameter, these are the parameter, mean vector and the shared covariance and the class prior are estimated from the data. Okay, since it explicitly assumes a probabilistic model with parameters, LDA is parametric. Okay, so option A is the correct answer. So this I have discussed it, like LDA is follow Gaussian distribution, and again it will have same covariance matrix. I have already discussed in the previous class during this LDA classifier, so you can just check or you can just see the slide of the previous class. So these are the thing, and each Gaussian distribution is nothing but a bell-shaped curve. So bell-shaped curve, you know, two parameters are important. One is the mean of the data and second is what is the spread. Okay, so spread is nothing but the sigma or the covariance. Okay, so LDA, as it talk about classes, so here it has shared covariance. Okay, same covariance matrix for all the classes. Okay, and then class priors already I have discussed what is class prior, what is this posterior probability, prior probability, that I have discussed in the previous class. So you can just check over the previous slides. Okay, so question number 4 has been done. So LDA is a parametric method. Again, it is a total theoretical question. Now question number 5, what is the common application of PCA in data processing? Classification, segmentation, dimensionality reduction. Option D, feature selection based on class labels. So any guesses for this? Common application for PCA? Come on. It is? It is used for dimensionality reduction, right? Very easy. PCA is used for dimensionality reduction. Option C is the correct answer. Classification, we do not say about classification because this is the limitation of PCA. It gives the maximum spread of the data, but it does not say about what is the separation between the two classes. So that is why this is false. Segmentation, again segmentation is related more to clustering, right? Segmentation is related more to clustering. Okay, clustering can be unsupervised. Yeah, PCA is also unsupervised, but it is more related to clustering and all that. Feature selection based on class level, again it does not do feature selection based on class levels. Okay, for feature selection based on class level, we go to LDE, okay, not PCA, okay. So this is the thing, classification. PCA itself is not a classifier. Segmentation, that's more related to clustering. And option D, that is feature selection based on class level, that's more for LDA, okay, that's more like LDA. So PCA, it is a unsupervised, does not use class labels, that is very important, and it is used for dimensionality reduction, okay. So option C is the correct answer. Most common application in pre-processing is to reduce the number of feature while retaining as much variance as possible, okay. So this is the total theory behind it. So this is I hope it is clear to all of you what I have told. Clear, right? PCA is used for dimensionality reduction, right? And LDA is used for feature selection based on this class labels, okay. So option C is right. Question number 6, consider the given samples for the two classes. X1 is this 1 2 3 4 3 4 5 5 data points for X1 class and 5 data points for X2 class. Compute both, that is within the class and between the class class scatter matrices, okay. So this you need to know the formula. So first you how you have to do, the step is first you have to calculate the mean, okay. So how you can calculate the mean? Mean is again very right, you have to add with the attribute, within the attribute, that is attribute is two attribute are there, one is X and another one is Y. So first we will be seeing about X, okay. So X, 4 plus 2 plus 2 plus 3 plus 4 divided by 5, and that will give 3, okay. So you can check 6 8 8 11 14, that is 8 11 plus 4, that is 15. 15 divided by 3 is 5, 15 divided by 5 is 3, because you have 5 data point, 1 2 3 4 5. So 5 data point, 15 divided by 5 is 3, okay. Similarly you can check for the Y attribute, 2 plus 4 6 9 9 15 19, 19 divided by 5, okay, that is 3.8, okay. So that has been written for mu. Similarly you can get the mean of this second class, that is mu2, okay. So mu2 also same way you can calculate. Once you got mu1 and mu2, you have to get this S1 scatter and S2 scatter, that is given by this two equation, okay. S1 scatter by this, S2 scatter by this, okay. That is the way, okay. So that is X minus mu1 and X minus mu1 transpose. So what is your X matrix? X you have to form. X is nothing but your data matrix formed by each attribute will be in this direction, that is rows, and each data point will be in column, okay. So it will be a this 1 2 3 2 cross 5, okay, 2 cross 5 matrix, okay. So 2 cross 5 you have to just subtract this and you have to get your S1 matrix. Similarly you have to get your S2 matrix. Once you got the S1 matrix and S2 matrix, what you have to do, you have to see this, that is from class matrix use a sample covariance denomination, that is n minus 1, okay. So just do this, that is 1 by n minus 1 divided by this scatter matrix, whatever scatter matrix you got. To get the sigma matrix, what you have to do, you have to do the 1 by n minus 1. So just do the 1 by n minus 1 and you can get the scatter matrix, okay. So you can get the covariance, you can better say it as covariance 1 and covariance 2. Once you got this two matrix, you can get your this, that is SW matrix, or the within class, okay. So within class matrix, that is nothing but sigma 1 plus sigma 2, that you can easily get it, okay. So once you got this, second thing is between the classes. So between the classes it is very easy, that is this mu1 minus mu2, mu1 minus mu2 transpose, okay. So mu1 you know, mu2 you know, just do the mu1 minus mu2 and then you do the mu1 minus mu2 transpose, okay. So by this we can get the SB, that is between the class scatter matrix. So we got the within the class, we got the between the class, and then we can check what is the answer, okay. So 3.3 minus 0.3 minus 0.3 5.5, so either it will be Okay, it has been written A B C D, so it should be A B C D, right? Not A, it should be A B C D, right? So I will just correct it, A B C D. Okay, so your answer would be, and 29.16, 20.52, 20. Yeah, answer will be nothing but A. Okay, this is your answer. So this is the formula regarding this regarding how to calculate the scatter within the class and scatter between the class. So these are the two main formula you have to keep in mind. These are the two main formula. Okay, this is the first formula, that is scatter within class, and this is the second formula, scatter between the class. But to get this, you have to just know what is this and what is this. This is for this you have to calculate this first. Okay, so this should be calculated by this formula. Once you got S1 and S2, just do the 1 by n minus 1 to get the sigma 1 and sigma 2. Once you got this, you can get the SW. Okay, so your option A is the correct answer. So is it clear how we find out? Any step, any doubt? No doubted. Question number 7, which of the following statement is true about the relationship between PC and LDA? PC and LDA both maximize class separability. PC and LDA both maximize variance. PCA maximize class separability, LDA maximize variance. PCA maximize variance, LDA maximize class separability. So guesses for this? Very easy, right? PCA maximize variance, LDA maximize class separability. So option D is the correct answer, right? Very easy. Because PCA, it always maximize variance, and LDA maximize class separability. Okay. So PCA and LDA both maximize class separability. Definitely it is wrong, because PCA does not have any link with any class. Okay, so that is why wrong. PCA and LDA both maximize variance. LDA does not maximize variance. It maximizes class separability because it is a classification problem. Okay, so that is why B is also wrong. PCA maximizes class separability, LDA maximizes variance. This is reverse. Okay, so that is why option D is the correct answer. Okay, so option D is the correct answer. PCA unsupervised. Unsupervised means unsupervised in the instance because it does not relate to any class. LDA supervised, it does class separation. Okay, so option D is the correct answer. Now this is the question number 8. Consider a dictionary 2D space following atom. This we have this 3 atoms. Okay, so the atoms means nothing but your basis vectors. For a given data vector or a given vector 2, 3, evaluate its representation using 2 atoms. The following dictionary following a orthogonal matching pursuit of the OMP algorithm. Okay, so how you proceed it? First, you have to multiply your vector. This is your given vector with all the pursuit, and check for which pursuit you are getting the maximum answer. Okay, maximum answer or maximum correlation. Okay, maximum correlation. So it is very easy. Like V into this, that is 2 plus 3, 5. Okay. So for first you are getting 5. For second you are getting minus 2 plus 3, that is 1. And for third 2 minus 3, that is minus 1. Okay, so definitely this is the first vector that you will choose. So just choose the first vector. Once you choose the first vector, what you have to do after that, you have to do this. Okay, that is you have to calculate the coefficient. Okay, because V minus alpha 1 A1. So to calculate the coefficient, you have to do this. That is 5 divided by A1 A1. V dot A1, that 5 we already have, and then have to do A1 dot A1. Okay, that is the magnitude of it. Okay, so magnitude of 1 1, that is magnitude of it, or just say A1 dot A1. Okay, not magnitude. Magnitude is with root, so that is not magnitude, but dot product of same vector, same basis vector. So by that your coefficient is 2.5. Once you got this, you can just write like this: V minus A1 alpha 1. So this is your residue. Once you got the residue, by this residue you have to check all the 3. Okay, and see for which you are getting the maximum thing. Okay, So maximum you are getting, I think, r1, that this is coming 1 and this is coming -1. So definitely -1 comma 1 you will select as your second thing. Okay, after this it is very easy. Once you got this, it is very easy actually. You, what you do, either you just do this, that is ATA inverse AT into V. Okay, so by this you can get your answers. Okay, so V is nothing but your this vector, and ATA inverse AT is nothing but A is nothing but whatever you will get by this, that is this is your first orthogonal vector that you have chosen, that is this 1 comma 1, and this is your second orthogonal vector that you have chosen, -1 comma 1. Okay, so this is your A matrix. So just do this calculation, that is AT into A, inverse of it into AT. Okay, so you will get into V, whenever you will do, you will get the coefficient. Once you got the coefficient, it is very easy to calculate. That is, this is the final reconstruction. So your final reconstruction is 2.511, 2.511, 0.5, -1 comma 1. Okay, so I think that is minus plus 5 minus yeah, so that is nothing but option A. Okay, so option A is the correct answer. So is it clear how we have done? Any doubt regarding this? Clear, right? Nice. So OMP is a greedy algorithm, dynamic programming algorithm, divide and conquer algorithm. So dynamic programming algorithm is your BP algorithm. Okay, so that is linear programming it does. So that is why BP algorithm is your dynamic programming algorithm, whereas MP and OMP, this is a greedy algorithm. MP is more greedy, OMP is greedy plus least square. Okay, so that is why option A is the correct answer. So OMP algorithm, greedy algorithm, used in sparse approximation. At each step, it greedily selects an atom, like we have just seen in this question. Like for each step, it is greedily select one basis vector, right? So that is why it is a greedy algorithm, most correlated with the current residue, right? Because the maximum answer that we are getting, maximum answer when we will get, it is most correlated, then only maximum answer we will get with the residue. Like 5 we are getting here and 1 we are getting here. So this is the second thing. Then it orthogonalizes the residue with respect to the selected atom. This repeats until a stopping criteria is met, that is fixed sparsity or the residual norm. So OMP is not a dynamic programming or a divider conqueror. It is a it's greedy. Okay, it is a greedy algorithm that is used in sparse approximation. So option A is your correct answer. Okay, so again it is a total theoretical question. So based on this question also, I have explained what I was trying to say. Okay, because each step it picks a vector, that is why it is a greedy algorithm. Okay, so this is the logic. Now question number 10, which of the following are true with respect to KSVD? It is dictionary learning algorithm for sparse representation. It generalizes the k-means clustering algorithm. It works on updating dictionary atom until convergence. Option D, all of the above. Again, all of the above, because we have just seen that it is a dictionary learning algorithm. I have told you it is generalization of k-means algorithm, because k-means algorithm is used for the first step when you are choosing a dictionary. Okay, so it is generalization of k-means algorithm. KSVD extends k-mean. So first step is k-mean. After that is KSVD, because KSVD is k-means plus your OMP or any other matching pursuit algorithm. Okay, and option C, it works on updating dictionary atom until convergence. So yeah, true, KSVD alternates between sparse coding and dictionary atom updates iteratively refining until convergence. So all are true. Okay, so this is the option D is the correct answer. Again, it is a total theoretical question. So this week you are getting more theoretical question, and numerical question you have only with PCA, and then you have this matching algorithm or projection of vectors into a particular basis. These are the three topics on which most numerical are based. Other is mostly theoretical theory for this week. Okay. So this is regarding this week. Any doubt and any questions? You can ask. Okay. So let me just show you. Yeah. Any doubt?
Yeah, so actually I missed the initial part of the session.
Okay.
So what this is about, like what kind of problems can be solved with these concepts?
It is probably dimensionality reduction. Nothing. This is the whole class. That is dimensionality reduction. Okay. Dimensionality reduction means like image, right? Image as how many okay, so each image has how many pixel, like n into n pixel, like 28 into 28 pixel, that is 784 pixel. So if you have like 60,000 image, okay, to train it in a deep neural network or anything, so you will have so many number of dimension, like 784 into 60,000. Okay, 784 into 784 into 60,000. Okay, so that is very difficult. So that for that, what we do, we do the dimensionality reduction. Okay, so this is the concept. So for dimensionality reduction, we have first seen the PCA, after that we have seen the LDA, and after that all is like to reduce the error. Okay, so if we are projecting any vector into certain number of bases, what we are doing, we are ignoring the other bases, right? So if we are ignoring the other bases, then there should be some reconstruction error, right? One is your actual data, one is your data you are projecting to a particular number of, you can say, axis or dimension, right? New dimension, not the original dimension, but new type of dimension, right? But there should be something error because you are not taking all of the dimension. So to reduce this, we have this different pursuit algorithm, like matching, pursuit, OMP, BP, etc. Okay, and third is regarding learning a dictionary. Okay, so whenever we are talking about pursuit algorithm, so we are just focusing on the vector that we are choosing, the vector, or in this it is called as atom, a basis vector or atom. Okay, so that is what we are focusing. But in learning the dictionary is nothing but the total number of all the total number of all the this atoms. Okay, so total number of, if we choose different type of dictionary, the type of atoms would also be differ. So learning a dictionary means first we should learn the dictionary and then we should choose the atom. So that is the KSVD algorithm. So this is the summary of the whole class. Okay, so let me just show you this code, it will be better for all of you. So yeah, so this is PC on MNIST dataset. Okay, so this is the code. So MNIST dataset. So MNIST dataset, you must have heard regarding this. So MNIST dataset is consists of this 70,000 grayscale images of handwritten digit 0 to 9. Okay, so 70,000 grayscale images. Okay, so many images. So each image is of size 28 into 28, so it has 784 pixel. Okay, so we reshape it into vector 784 comma 1, that is 784. So each image has this 784 dimension. Okay, 784 dimension each image. Okay, now if all these dimension are taken for neural network and etc, it is very tough. Okay, to it will have more time for training, and it will have more computational complexity. Okay, so to solve this, what we will do, in place of this 784 dimension, we will project all this vector into a different dimension and see how many dimension we should take to get the maximum variance. Okay, so for that we have just computed the covariance matrix. So this is how PCA works, right? First we center the data and then center the data. This is centering the data, then compute the covariance matrix, and then just do the find the eigenvector and eigenvalue for this covariance matrix. Okay, so by this, what is our target? Our target is uh, target is to retain as many principal components so that we will get variance of more than 95%. Okay, so let me show you by this graph. This are your principal component. Okay, so to get more than 95% of data, we can see we have to go to like 140 to 160. Okay, 160 principal component we have to conserve to get more than 90% of variance. Okay, so one thing is this. So very easy, whatever I have solved in the question, this is the same thing. Okay, but to have more visualization, this is the original image. Okay, and other we have this reconstruction error. So if I am taking only one PCA, if I am taking only one PCA, then you can see this is the error, that is 0.06 is your reconstruction error. Okay, like this. So you can see this picture is very blurry because we are taking only one principal component. We have this 784 principal component, but our idea is to retain 95% of variance. So that is why to retain 95% of variance, we had to take like 150 or 155 principal component, right? So to if I just make the image with one principal component, I am getting very much more reconstruction error. So you can easily see this is the original image, and if I am reconstructing the image with only one principal component, this is very blurry. You can easily see this is very blurry. And after, if I take 5 principal component, our error certainly decrease. This is 10, this is 5. Okay, so our error, you can say 0.58 is our error. So this is the error. Okay, so this is the error. So now it is something visible, but again we cannot say what exactly it is. With 10 principal component, the we will have less reconstruction error. 10 is something like here. Okay, 10 is middle of this, so something like here. So we are getting 0.04 reconstruction error. So now also we are getting some shape, but again it is not clear. Then this is with 20 PCs. This is with 50 principal component. With 154 principal component, we are getting 95% of variance. So with 784 is our actual dimension, but with 154 principal component only, we are getting the 95, more than 95% of data. So this we can use for, so you can easily calculate 784 minus 154. Okay, so that is coming around how much? Coming around 630. So we are eliminating 630 other principal component. We are only taking 154 principal component, and by this only we are getting a good image that we can see. Okay, and so this is regarding one image. Okay, so we are reducing 784 minus 154, that is 630 principal component or 630 dimension for one image. Now imagine for 70,000 image. Okay, so that is 70,000 into 630 dimension we are reducing. Okay, so we are reducing a lot more data. So this is the whole concept regarding PCA. Okay, so I hope it is better clear with the help of this code. Okay, so by this I am ending the session for today. Okay, so we will meet not on the next Friday, because next Friday is definitely a holiday, and we will meet on the next Tuesday. Okay, so
Sure.
that I am planning for the 12th class, and after that I will take one extra session on the next Friday. Okay, and by this I am ending my course. So by this I am ending the session for today. Bye everyone.
Thank you. Bye.